So you can think, if you like, in terms of determining the values of the C's. You can say, well, experiment tells me the values of the scattering length of the R0, and that's indeed true. So this equation that C0 hat is equal to A, you could view this as a matching equation. Putting back the M, we have that. And then for C2 hat, we have R0 over 2 A squared. So pretend that experiment gives you R0. And A, which they do measure, and then you know the value of your Wilson coefficients, and you can start using this theory. Now, if you think about the power counting, then if A and R0 are of order 1 over lambda, that's the natural thing you'd expect, then you reproduce what we expect. Whatever it was a minute ago. It's 2m plus 1. Okay, so if all the constants are scaling like whatever their dimensions are, in this case they're both dimension -1 in momentum units, then you would reproduce exactly this power counting that we said. Okay, so everything would be nice. But nature was not so nice, or nature threw us in a different direction. When we actually look at the value of these constants, the scattering length is large. So C0 is large from this point of view. So let me quote some numbers for you. So in the 1s0 channel, which is the larger one, this guy is 23 Fermis. And in the 3s1 channel, it's 5 Fermis. And both of these are actually large. And we know they're large. Look at the errors. If you want to think about momentum units, you could take 1 over A. And for this guy here, taking 1 over A is giving, like, if I did the calculation right, minus 8.3 MeV. Oh, sorry. No, that's this guy. And this guy here is giving 1 over A, which is 36 MeV. So if you thought the natural size was the pion, then you'd say, well, these constants should be 1 over m pi. That these numbers that are in MeV should be in pi. And 8 MeV is a much smaller number than 130 MeV. 36 is also a smaller number than 130 MeV. So both of these guys are not natural. In particular, this one you see is quite non-natural. So there's a fine-tuning going on, some kind of fine-tuning from the perspective from our dimensional counting EFT point of view. There's a fine-tuning that's making the A big. And if you look at the other guys, the R0 and the other guys, they are exactly of the size you'd expect, so there's no fine-tuning there. So the only fine-tuning is in A, and not the other ones, just by comparing to data. Okay, so how do we deal with that? It looks like we set up a defective theory. It seems like a beautiful theory. It could describe some things about quantum mechanics, but then we learned that our power counting sucks. So what we want is actually a power counting that's a little different. where AP is of order 1, or even AP much greater than 1. We'd like that to be allowed, where R0P is much less than 1. We'd like to be able to take the scattering length effectively into account to all orders, and that means basically that we want to treat C0 as relevant. We don't want 8 MeV to be the limit of the thing that goes downstairs when we're making a power expansion, right? We'd like something like M pi to be downstairs. If you want M pi to be downstairs, you've got to treat AP to all orders. And then you're just limited by M pi, which is the R0 term. And that means you've got to promote C0 from being irrelevant, scaling like 1 over M lambda to something that's relevant. So this is actually a problem that occurred because we just proceeded and started calculating, and we used effectively the MS bar scheme in dimensional regularization. We saw power subtractions, we did nothing. So let's try another scheme. It's a little more physical, called off-shell momentum subtraction. So what is off-shell momentum subtraction? It says take the amplitude, and in this non-relativistic theory, you take P to be at some imaginary point so that you would avoid any cuts. And you can define, in whatever channel we're in this mu r scheme, you can define the amplitude at that particular point to be the tree-level result. Okay, so any loops, if you take them at this point, you should get back that result. So this is the analog of what you'd do in a relativistic theory, where you would take p squared to be minus mu squared. In the non-relativistic theory, it's always p that's showing up, which is the 3-vector p, magnitude of the 3-vector. So we should assign some rule for that. And it's just, we take it to be I times mu. So how does this change our calculation? So let's go back to this one-loop calculation. So now there's going to be some counterterm needed. It's going to be a finite counterterm. So let's see what it does. So the loop graph gave this, IP. That's what this graph gave. And this has to be just such that if I set p equal to I mu, that I get 0. So this has to be plus mu. So the counter term is giving mu r C0 squared. And that exactly makes this amplitude vanish at that point. And that's what you want, because the tree level graph of the C0 is already giving the right condition. OK? Is that clear to everybody? This is the correction to this. The tree level graph in the amplitude here gave minus IC0, so we already got what we want. When we go to one loop, we just want to make sure it doesn't contribute, and that forces us to put the plus mu there. And so what this mu is doing, it's tracking the power divergence that dimreg within MS bar did not see. The integral is power law divergence, and our cutoff mu r has appeared in the numerator and has tracked that divergence. So we're doing the standard thing here where we split the coefficient into the bare coefficient into a normalized and counterterm piece. And unlike MS bar in this particular renormalization scheme, there's a finite correction there. And we have a renormalization group equation. And if you work out what that is from the counter term, it turns out that only this one loop, it's one loop exact. Showing that is a little more work than I've done. But it turns out that the beta function is one loop exact. Higher order bubbles don't give any contribution to this beta function, and this is the anomalous dimension. So we could just calculate all those bubbles, impose the same type of thing, and I've given you a reference that does that. So there's a renormalization group equation in this scheme, which we didn't have in MS bar. In MS bar, it was scale independent. We also have a connection to the MS bar scheme, because if mu r was 0, that corresponds to the MS bar result, right? So C0 of 0 is where you can think of putting your boundary condition, which is matching to the experiment, which is the A. And the advantage of this off-shell subtraction is that we have a mu, and we can go somewhere else. And if you look at the solution of the RGE with that boundary condition, you see something interesting. So this is the result for the coefficient. 1 over mu r minus 1 over a. So if mu is of order p, which is much greater than 1 over a, like we want, then the right counting for the c, which is a function of mu, is 1 over m mu. OK? And so what we've done here is we've swapped 1 over the physics scale that we're integrating out for 1 over the scale mu, which we're taking to be of order the physics we're keeping. OK? And this is relevant now. This is a relevant coupling with that change. We've made it much bigger by just switching to this physical renormalization scheme. And if we take mu of order p in that scheme, this all of a sudden becomes an order 1 effect with leading order in the Lagrangian, because we have effectively p's downstairs in the coupling. Okay, so this scheme allows us a way of thinking, in the effective theory way of thinking, of having a power counting where we'd have to keep this C0 to all orders. Yeah, AP is order 1. So, so if you look at the Lagrangian, then you have to go through the counting of how many powers of p the nucleon field has, which you could do in the same way that we did with the mass. And if you do that with the 4-nucleon operator with an extra power of p downstairs, you will find that it has the same p scaling as the kinetic term. OK? I didn't go through that, but.
So that justifies this even when p is not much bigger than 1 over a? Is that what you're saying?
Yeah, so if p is much bigger than 1 over a, or p is even order 1 over a, which is a sort of also, yeah, it's also fine with this counting. If p is of order 1 over a, these two terms are sort of comparably big, but you could also use this approach for that case. As long as you're not in the case where p is much less than 1 over a. So if you're in that case, then you should really think about expanding this out in some sense, and then you're getting back to the MS bar result. The MS bar result would have been fine. But to get away from the MS bar result and think about physics mu of order p, we could use this scheme instead of MS bar, and then we actually see that we get a reasonable power counting.
I guess my concern was, what about when mu is like, yeah, what about this pole, but you can always just
Yeah,
choose mu.
we'll talk about the pole. Yeah. Coming up. All right. So it's interesting to think about this from a renormalization group point of view, which is kind of what I was doing when I wrote down a beta function, but here was just after this solution, because from that solution I get the power counting that I want, which is that the C0 term is the same size as the kinetic term, and both are relevant. So we could do that just like we counted p's for in chiral perturbation theory, or just like we counted, just comment. These guys are all relevant, as long as we count this mu as 1 over p, and 1 over mu is 1 over p. So there's another way of thinking about this and thinking about these different cases, and that's just to think about the beta function itself. So if we look at the beta function for this C0 coupling, and we just put in the solution, plug this back into that equation here, it's some constant out front, and then it looks like this, a times mu 1 minus a mu squared. If we want to talk about all possible values of a, well, a can go from minus infinity to plus infinity. So it's useful, if we want to draw this, to map it to a compact interval. So let's do that. The tangent. And let's just plot beta as a function of x. So there's 3 values actually where beta vanishes. There's 1 value where it blows up. So this is, here is x equals minus 1. This is x equals 0. This is x equals plus 1. And what it looks like dips down here, there, blows up, and it comes back down and goes like that. So that's what the beta function looks like. So this point here corresponds, if you think of being at fixed mu, say you're studying the physics at fixed mu, this point corresponds to a equals minus infinity. This point corresponds to a equals 0. And this point corresponds to a equals plus infinity. So there's 3 points where the beta function vanishes if you think about A space for fixed mu. Well, use some color. So you can ask about nature. So nature told us the value of A, so what does that correspond to? So taking some value of p and mapping it to some value of x, kind of generically the kind of point that you're interested in is here. This is A1S0. Sits there, and then A for the 3S1 would sit kind of here. So what's going on in this case is that you're not near this fixed point. You're actually close to this one. And you're not near this fixed point. Well, actually, there's an infinity in between. You're closer to this one. This size, as you should think of, as this 8 MeV, generically, and then this is like the 8, but there's also a pole in between. So 3 fixed points. When we do perturbation theory, we expand about fixed points. And you can, one way of saying what was wrong with dimensional analysis was it was just expanding about the wrong fixed point, the pink one. So A equals 0 was the non-interacting one, where we just have the relevant interaction being the kinetic term, but none of the interaction terms are relevant. And A equals plus or minus infinity are interacting fixed points, where we have an interaction that's relevant. So you can think about that in the following sense. Classically, what A is measuring is kind of the interaction size. You know, if you have classical scattering, your cross section's 4 pi a squared. And if A is small, then you're, if A is either very small or very big, then basically it's the same on all scales, because you can't, it's either infinity or 0. It looks the same to all particles of all different momenta. Okay? And that's one way of thinking about these fixed points, that the physics can't, the physics, yeah, just what I said. So what about this infinity? So that's also interesting. So when A is 1 over mu, beta goes to infinity. And this actually, there's a reflection of this in the theory. It corresponds to a bound state. Which I think we'll talk about next time. But So there's a bound state in the theory, and actually if you start from this side, you can never see that bound state because you're doing perturbation theory. You don't see perturbation theory in bound states. If you start from this side, the bound state is actually just in the theory. We'll talk about that next time. And so it's a state in the theory. You can go and you can find the pole in your amplitude. It's just there. It corresponds to a physical state of this spectrum, and it's called the deuteron. So we have a non-interacting theory. We have some non-trivial amplitude, and this deuteron is a pole in that amplitude. And you never see a pole if you're just doing perturbation theory. And if we actually look at the energy, the binding energy of this state, it's also small, uncharacteristically small. And it's actually related, the fact that the binding energy is small is just related to sort of the size of this A. Talk about that next time. So what I was saying before about the theory at all scales looking the same, when you have A equals 0, of course, it's non-interacting. Or when A equals equal to plus minus infinity, it looks the same at all scales. That means it's scale invariant. So it's a scale invariant theory when A is at these fixed points. And something I worked on was the fact that these points are actually conformal fixed points. So that there's a conformal symmetry of the theory that exists at those points. We'll talk about that a little bit. There's another symmetry too, which I have to mention. And not only because I also worked on this one, but because it's good to enumerate all the symmetries. There's actually a combined spin-isospin symmetry that turns into an SU4 in this limit. So much like in heavy quark effective theory where the mass was big, new symmetries popped up. Same thing happens here when the scattering lengths go to infinity and you go over to those fixed points. There's new symmetries that pop up. One's a conformal symmetry and the other one's a spin-isospin symmetry. All right.